Hi everyone, this is going to be the second lesson on the topic of mechanics for GCSE Physics students. In the last lesson we introduced the concept of forces and resultant force. We defined quantities as being either scalar or vector quantities, and we reviewed some of the ideas concerning Newton's laws of motion. We're going to be coming back to all of those and exploring those in a lot more depth over the course of this section of the course. But in this lesson we're going to look at an idea that we'll also develop a lot more later on in the topic on energy, which appears at the end of this GCSE Physics course, the concept of work. So let's take a look at the learning outcomes for today's lesson. So by the time you've gone through this teaching video, and if you're enrolled on this course on my website, by the time you've also completed the other learning activities on that lesson's page, on this lesson's page, you should be able to do the following. So firstly, we need to define work in a rigorous mathematical manner, and as we'll see, it's defined in terms of a force applied and the displacement that that force causes along the same line as the force acts. We will also need to be looking at some examples of using that formula, that equation, to perform various calculations. And finally, we're going to look at a couple of ideas concerning different ways of categorizing work. Now, these ideas we'll talk about very briefly in this lesson, but as I say, there is an entire topic on energy towards the end of this course, where we talk about these ideas in a lot more depth. And so, though we're introducing these ideas in this lesson, they will be expanded upon in later lessons of this course. So, in order to talk about work, we need to talk a little bit about energy even before we've encountered the energy topic. So we've already encountered the concept of energy in previous lessons of this course. For example, we talked about the energy transferred by electric current in the first topic on electricity and so on. And we've mentioned before that the idea of energy is summarized in the law of conservation of energy, which states that, usually stated something like this, that energy cannot be created or destroyed, but it can be transferred or stored by means of various phenomena. So in other words, energy can only be stored or transferred from one phenomenon to another, which can either be within the same system, or from one system to another, or from one system to its environment, and so on. So energy can only be stored or transferred. Now, energy is defined in a qualitative sense, at least at GCSE level, usually something like it's the capacity to do work. So energy is often defined verbally as the capacity to do work, but work is often defined verbally as the transfer of energy. And so the two concepts are very intimately related, and we're going to be expanding upon them both in that later topic on energy. For now, it's enough to say that the total amount of energy that you start with before some change takes place to a system or an object, it's exactly the same amount of energy as you end up with after that change has taken place. Now, what this means on a wider scale is that the sum total amount of energy in the universe can never be exhausted, and it never really changes in the total amount of energy, but that energy can become very spread out. So work is often defined as a transfer of energy. So when energy is used by devices, and I use perhaps I should put the word used in air quotes here, but when energy is used, it's not destroyed, it's transferred into other objects, into other phenomena. So at a very basic level, and again I'm simplifying things somewhat here, if we have a steam train, then the coal that's burning in that steam train represents a store of chemical potential energy which is being released as heat energy. And the heat transfers that energy to the molecules of water in the boiler. Those molecules will heat and get hotter, and the liquid water will become steam under high pressure. The steam is then responsible for driving the whole train forwards, and so it gets transferred as mechanical kinetic energy. So the overall energy transfer that occurs is from chemical potential energy in the coal to heat energy to mechanical kinetic energy of the whole train. Now, there are other transfers that are taking place here as well, because we are simplifying somewhat here. Not all of the heat energy generated goes directly into heating the water into steam and driving the train. Some of it is radiated and conducted into the surroundings as wasted heat. And of course, you still have some of the chemical potential energy being released within the boiler as light energy. And obviously, the steam train also produces a fair amount of sound as well. So energy transfers for complicated machines like this in the real world are seldom as simple as is being represented here. So, taking another example then, if we have a wind turbine, such as one of these, the intended purpose of this is to change the kinetic energy of wind into useful electrical energy. And so that's the intended energy change. That's the energy transfer which we build the wind turbine to do. But there are other transfers taking place as well. So, for example, these wind turbines often will produce a lot of sound, and it will also lose some of its efficiency, in the sense that not only does it transfer some of the kinetic energy as sound, but it also transfers some of it as thermal energy in the workings of the generator unit and the moving parts, and that gets eventually conducted away and radiated into the surroundings as well. So these are the typical kinds of energy transfers that you might encounter, but in all cases, whether you're when you consider the useful energy being transferred, but also the less useful or wasted energy transfers, the total amount of energy you start with is always equal to the total amount of energy that you end up with. And this is the law of conservation of energy. That's what it states. So if we take another example here, of a person doing work, and I'm going to talk about work initially here at a very instinctive level. So when we lift a weight, we are doing work on that object. We are transferring energy to that object, and so we can define work verbally, qualitatively, as the transfer of energy. So when energy is transferred to an object, we say that work has been done on that object. So, for example, a person training in the gym using weights like these can only do work if he or she has energy with which to do that work. This type of weight training involves the transfer of energy from chemical potential energy stored in your muscles to kinetic energy, to eventually to gravitational potential energy, because you are lifting the weight to a higher height above the ground. Now again, we're going to be talking about kinetic energy and gravitational potential energy a bit later on in this topic, and also in the energy topic. Now, this is not to say that these are the only energy transfers taking place. Some of the energy that you started with in your muscles ultimately is transferred in less useful ways. So skeletal muscle, even highly trained skeletal muscle in athletes, is only about 25% efficient, which means only 75%, or rather 75% of the total energy that you start with in your muscles gets radiated away into the surroundings as heat energy, and only 25% of the energy that you started with actually gets usefully transferred as kinetic energy when you move. So let's take a look now at work done. So instinctively and qualitatively, we can define the amount of work being done in terms of the amount of energy being transferred. So and there is an equation which defines this relationship. So before we rigorously define what this means and why this relationship is the way that it is, let's take a look at it here. So the work done, the energy transferred, the units of that must be in joules, because we're talking about a certain amount of energy that has been transferred from one object to another, or from one system of objects to another system. And so work, like energy, has units of joules. Now, to calculate the amount of work done by a force that moves an object, it's the force in newtons that's doing that movement multiplied by the displacement of the object along the same line as the force that's acting. And that's in meters. The standard units of displacement, the magnitude of displacement, is in meters. So energy and work are both measured in joules, and we define 1 joule of energy as the energy transferred when a force of 1 newton moves an object by a displacement of 1 meter along the same line as the force, parallel to the force. So Often you'll see this equation and you'll see this mentioned as distance because it assumes that the distance being measured is the distance that the object moves along the same line as the force. Now in a moment we're going to take a look at this in a little bit more detail and look at the slightly more rigorous definition of this to include forces that act at an angle to the displacement. But let's keep it simple for now. So this is the equation that you'll see in many GCSE Physics specifications and also in GCSE Physics equation sheets. So if you have trouble rearranging it, you can use one of these diagrams here. You can use this formula triangle. So if work done is equal to the force multiplied by the displacement, then to rearrange this equation for the force, we would divide both sides by the displacement to get this. If we wanted to rearrange the equation for the displacement, we would divide both sides of the equation by force to get this. So you can take this equation and rearrange it to give a couple of different variations on that formula. So let's look at some very basic examples here. And again, I have some students in the Zoom room with me here, and I realize you guys have asked a number of questions concerning the more complex examples on the lesson page for this lesson. I will be going into the idea of work and forces in a little bit more depth in a moment, but for the moment, let's take a look at some basic examples and then we'll build up from there. So a lawnmower is pushed 100 meters with a force of 30 newtons. So how much work is done by the person who is pushing with that force? So I'm going to pause here and let you guys respond in the chat. And if you're watching this on my website as a recording, the video will pause and you'll be able to answer this question in the interactive pop-up. If you're watching elsewhere, such as on YouTube, again, just pause the video and see if you can work this out for yourself, and then unpause the video to see the solution. Okay, so I'm already getting some pretty quick responses here. It's a pretty straightforward problem. Yeah, so let's go through how this is done. So again, in this case, we're trying to work out the work done. Both the force and the displacement are in standard units, which is important if you're putting values into an equation. You want them to be in standard units, otherwise the answer that you get may not be correct. So in this case, this is the equation we're going to use. Work done is equal to the force times the displacement. In this case, we can now substitute the force and the displacement from the values given in the question. We can evaluate this, and we find that the amount of work done is 3,000 joules, or 3 kilojoules. Let's take a look at another basic example here. So, if a person does 6 kilojoules of work to push a car by a distance of 20 meters, how much force does this person use to move the car? So again, I'm going to pause here and let you guys have a go at this. Again, it's a fairly straightforward example, but we'll build up to some more complex examples in a little while here. Okay, again, some pretty quick responses here. Just going to let a few more people chime in. Okay, good. All right, so here's how we do this. So in this case, we're trying to work out the force. So we would need to rearrange this equation to make force the subject. We divide both sides by the displacement and we get this. So the force in this case is the work divided by the displacement, and the force in this case is 6,000 joules divided by 20 meters, the displacement. Now again, notice in the question, the work done was given in kilojoules. You must convert this into standard units of joules before entering it into the equation. So the force in this case is 6,000 divided by 20, which is 300 newtons. So at a very basic level here, we can see that there are two factors which affect the amount of work done. So if we move an object along a surface and the resultant force that's acting is 12 newtons and the force moves a distance of 24 meters, we can see that the total amount of work done by that force on the object is 288 joules. It's 12 newtons the force multiplied by 24 meters the displacement. Now if we increase the force and slightly increase or decrease the distance here, we use a larger force of 18 newtons and a smaller distance of 16 meters, we can see that we get the same amount of work done. If again we reduce the force and we increase the distance from the original value of 24 meters to 32 meters while decreasing the force from 12 newtons to 9 newtons. Let's see what the effect of that is going to be on the work done. So we see here that the work done depends upon the force and the distance moved along the same line as the force, parallel to the force. So let's take a closer look at the concept of work and give a slightly more rigorous definition of what we mean by work. So far I've been mentioning force and displacement, and I've been using them in a kind of GCSE level basic version of this equation, which doesn't take into account the idea that both of these are in fact vectors. The force is a vector and the displacement is a vector quantity as well. So let's think about this situation here where we're sliding forces, we're using forces to move objects over different distances and changing the force and also changing the distance. Let's take a look at what that means for the concept of work in a little bit more detail here. So let's say we have a block placed upon a frictionless surface. Now we're using a hypothetical example here of no friction. Just to make things simpler for ourselves. Later on we'll deal with examples concerning friction in later lessons, and also in a number of the more advanced examples that occur in the interactive quizzes on the lessons pages for this course. But for now, let's keep it simple here. We have a block, and let's say this block is moved parallel to the table surface by a small force. Let's call this force lowercase f. Now again, the force is a vector. We're going to be exploring that in a bit more depth in a little bit later on. Now let's say that this force, little f, moves this block a relatively short distance here. Let's call this displacement lowercase d. So imagine a situation where you are pushing a car and you're pushing it with a relatively low amount of force and you're pushing it a relatively short distance. Well, instinctively, intuitively, we imagine that you're going to be doing less work, you're going to be transferring less energy, you're going to be making less of an effort to do this than if, for example, you were to take that same force and move the same car a much greater distance. So rather than just moving it this short distance, let's say you applied that same force and you moved it a much greater distance. Let's call this capital D. And again, you're moving it with the same amount of force that you were using before. So this situation here involves a greater expenditure of energy on your part to do that than the situation before it. So we can see instinctively that there's more work involved here than here. Now let's take the first situation again. Let's think about this same situation, but this time, rather than expending a relatively low force, you push with a much larger force. So let's call this capital F. But again, you're moving the same amount of distance that you were before, a relatively short distance. Let's call this lowercase d. So if the distance that you're moving is the same as before, but you're expending a lot more force to do it, again, intuitively, from our own experience, we know that that's going to require a much greater degree of effort. You're going to transfer a lot more energy in the course of doing this than if you were to expend, or if you were to apply a much lower amount of force and move that object over the same distance. Now let's look at this example again here. So if we were to, in this case, apply a larger force, this same larger force, capital F this time, to move this object over that much greater distance, capital D, displacement capital D, then this situation here would involve, of all of the situations we've discussed, this situation here would involve a much greater expenditure of energy, a much greater transfer of energy than the previous three situations. You're pushing with a much greater force, you're pushing with that force over a much greater distance. So at an intuitive level, the concept that work is related to both the force which is being applied and the distance over which that force acts, or over which the object moves along the same line as the force, that is fairly intuitive. It's a fairly instinctive idea. So far, so good. Fairly instinctive. However, so far we haven't really changed anything about the block itself. So what happens if instead of pushing the same block, you now push a much larger block? So let's say rather than a block of a small mass, let's call this small mass lowercase m, you're now pushing a block with a much larger mass. Let's say you push it with the same amount of force that you had in that first situation, lowercase f. And let's say you also move it through the same distance as you moved it before, lowercase d. Now, in this situation, what's going to be the difference between these two situations in terms of the work done here? Let's explore that in a little bit. Let's take a closer look at that. Now, remember that we are transferring energy, we are doing work on this object. A change is taking place to this system of this object sitting on this frictionless surface in all four of these situations. So, if we think about it carefully, before the force begins to act, the object is stationary. By the time the force stops acting at this point, the object will no longer be stationary on this surface. Now, the relevant law from Newton's laws here is that the force that's acting, and the force is a vector, so we use the vector symbol here, is equal to the mass multiplied by the acceleration, and the acceleration is also a vector. Now, since the force and the acceleration in all of these examples are in the same direction as each other, they are parallel to each other, we don't need to do anything complicated with vectors here. We can simply say that the magnitude of the resultant force that's acting in each case, and to show magnitude we draw bars on either side of a vector quantity like this. The magnitude of this force that's acting is going to be equal to the mass multiplied by the magnitude of the acceleration. Now, what this means for these two situations here, when we're comparing this situation here with a smaller mass to the same situation, the same force, the same displacement with a larger mass, is that in both cases, the mass, the force is the same, the resultant force is the same, but the masses are different, which means that by the time this force has acted displacing this object over this displacement, the object is accelerating the whole way. But because the mass here is smaller, the acceleration is going to be larger as a result of this. The amount of acceleration produced by a force is dependent on the mass on which that force is acting. The larger the mass, the lower the acceleration. So in this case, we're going to get a relatively rapid acceleration here. Let's call that capital A. In this case, with a much larger mass, if the mass is much larger and the force is the same in both of these two instances, then to calculate the acceleration, we divide both sides by mass. Since we're dividing by a much larger mass, the acceleration will be much less. So in this case, the acceleration, we'll call this lowercase a. So what this means is, by the time this object reaches this point here, it's going to be traveling at a lower speed, a lower velocity in this direction than this, or rather a larger velocity in this direction than this object here. This object here, because it has a larger mass, it experiences less acceleration for the same amount of force acting on it over the same displacement. And so the speed, the final speed when it reaches this point in its journey is going to be much less than in this instance here. And so in both cases here, the work done is actually the same. From the point of view of the pusher, you are pushing with the same amount of force over the same distance. And so from the point of view of the whatever object or person is applying this force, the same amount of work is being done here. The effect of that work on the system is different because the system is different, but the work being done only depends upon the size of the force that's acting and the magnitude of the displacement that force produces parallel to the direction that the force is acting. So all of these examples have been using the idea of a force acting parallel to the displacement. But what happens if the force and the displacement are at angles to each other? Well, let's start with the example of the force acting perpendicular to the displacement. And let's see where that leads us here. So we have an object on a frictionless surface, And we have, in this case, a force. Let's just say the force is acting directly upwards. It's acting perpendicular to the fact that the displacement that the object is undergoing. Now, the object is being displaced in this example. It, for example, may be moving with constant velocity along this direction here, along this frictionless surface. Let's say somebody has pushed it before this force started to act, and the object is simply moving along this surface at a constant speed. So this is our displacement, and let's call it capital D because I've drawn a bigger displacement. It doesn't really matter what the size of the displacement is here. And let's say this force that's acting is not changing the orientation of the object. It's not pulling the object off the surface. It's simply acting perpendicular to this displacement. Now the question here is, does this force do any work on this object? So I'm going to pause here and let the students in attendance answer that question. Does this force in this example, which is acting perpendicular to this displacement, do any work on this object? Okay, some mixed answers coming through here. All right, so let's think about this situation here. The object is moving at a constant speed in a constant direction along this displacement vector here. So this is the displacement. It moves from here to here. Now the force that's acting is not changing the path of the object. It is not in any way affecting this system in terms of its motion. And so the correct answer here is that it does no work on this object. It is not changing the system in any meaningful way here. It's not altering the motion of this object. It's not producing any acceleration or any other effect along the line of the displacement. So in this case, the work done by the force is zero. Now again, it's zero because again, the idea here that we've already encountered at a basic level is that the work done is the force multiplied by the displacement which occurs parallel to the force. Now, since the force is perpendicular to the displacement, there is no component of this force which acts parallel to the displacement, and so the work done by this force is zero. Now, we're going to expand upon this when we give the rigorous definition of work done here, which we'll, in fact, let's do that now. So let's imagine we now have this situation here. We have an object, and it doesn't matter, as we saw before, it doesn't matter in terms of the work done by a force what the mass that force is acting on is. It can be a small mass, it can be a large mass. It doesn't really matter in terms of the work done by the force which is acting on the mass. What the mass will affect is the outcome of that work being done. So as we saw, the smaller force acting on this, or the force acting on the smaller mass, produces a greater acceleration than the same force acting on a larger mass over the same displacement, but the amount of work being done is the same. So it doesn't really matter what the mass is here, but let's just say in this instance we have a force which is acting at an angle to the displacement. So if the displacement occurs along the horizontal like this, let's say that the force instead acts at an angle to the horizontal. Let's call that angle theta. So we have this force acting at this angle. So how do we determine what is the work done by this force? So if this force is causing this displacement, but it's acting at an angle to the displacement, how do we determine what is the work done in this instance? Well, for this, we need to go back to this idea that forces are vectors. And so a vector can be resolved into its components. So to illustrate that, let me just use a slightly different color here, because we're going to need to refer to an idea from maths, which hopefully you've encountered already, the idea of basic trigonometry. So let's imagine that a person takes a journey here. Let's say a person takes a journey from A via this point B to this point C. So their journey is the first leg of their journey can be represented by the displacement vector AB. Now again, in maths you would represent this like this, AB. And then the second leg of their journey involves a movement from point B to point C. So this would be BC, vector BC. However, this journey involving these two vectors can just as easily be performed. The outcome can be arrived at by means of a third vector, AC. So in this instance, and this is probably something that you've come across when you were studying vectors in maths, the vector AC is equivalent to, it's equal to the sum of the two vectors AB and BC. So whenever you have any vector quantity acting at an angle, you can think of it as being equivalent to two separate vectors, one of them acting along the horizontal, one of them acting along the vertical. So in this case, vector AC is equal to the sum of vectors AB and BC. And this is true for any vector quantity, whether you're describing displacements involved in a journey, whether you're describing forces, for example. This force can be thought of as two separate forces, one of them acting along the horizontal, one of them acting along the vertical. And we're only interested in the force that's acting along the horizontal because that is the component of this force vector which is causing this displacement. The force vector, the component of this vector acting upwards, does no work on the object because the displacement is along the horizontal. So we can resolve this force vector into two separate components, one of them which acts along the horizontal and one of them which acts along the vertical. So we can say that if this component of this vector that acts along the horizontal is the component of this force, the horizontal part of the force, if you like, this is the one which is responsible for this displacement. It is parallel to this displacement, and therefore this is the part of the force, this diagonal force, which is responsible for this displacement, and therefore is the part of this force which is actually doing the work on the object. Now, according to trigonometry, when you have a right-angled triangle like this, again, basic trig. So when you have a right-angled triangle, the diagonal is called the hypotenuse. The angle that we are referring to, theta here, the side which is opposite that angle is called the opposite. The side adjacent to the angle is called the adjacent. So what we're interested in here, of this right-angled triangle here, is this component which corresponds to the adjacent of this right-angled triangle. So if you remember from trigonometry, the cosine of the angle theta, cosine of theta, is equal to the adjacent, the length of the adjacent divided by the length of the hypotenuse. And so in this case of this right-angled triangle, this force vector along the diagonal represents the hypotenuse of this triangle. The component, the horizontal component of this force, represents the adjacent. So we can write this expression here, cosine of theta for this force, this diagram, this right-angled triangle, is equal to the horizontal component of this, which we'll call f sub x. So this is the component of the force vector which acts along the horizontal. This is the component which acts along the vertical. Let's call it f sub y. But this component which pulls upwards on this object is irrelevant to this problem because it contributes no work to this situation. So we're interested in this one. So the cosine of this angle theta by trigonometry is the horizontal component of the force vector divided by the magnitude of the force vector itself, the hypotenuse. So if we rearrange this equation to find an expression for this horizontal component, we find that f sub x equals to the force, the full magnitude of the force multiplied by cosine theta. Now these are all vectors. So if we're using proper notation here, we should be putting arrows on the tops of these. However, we're only interested in the magnitudes of these. So we'll put magnitudes around these. So what does this mean for our problem then? How do we calculate the work done by this force acting at a diagonal, at an angle to the displacement? So going back to the problem then, we now know an expression for the magnitude of the force which is responsible for the displacement. Remember, in general, the magnitude of the work done is equal to the magnitude of whatever force is acting. So if we're going to be rigorous about it here, it is the magnitude of the force acting multiplied by the magnitude of the displacement. And these two need to be parallel to each other. Well, the magnitude of the force that's acting parallel to this displacement is F sub x, which is this. So in this case, the work done is F, the force, the magnitude of the force, in this case operating at an angle, times the cosine of theta. Now this is multiplied by the magnitude of the displacement. So we can write an expression here. Let's make a bit more space on this side. So work done is equal to the magnitude of the displacement here multiplied by the magnitude of the force times cosine theta. So what does this mean then? Because now we've actually generalized a situation which includes forces which are parallel to the displacement and forces which can operate at an angle to a displacement. Well, what we've found here in this equation is that the work done is equal to the magnitude of the force multiplied by the cosine of the angle between the force and displacement. So that's F bar, or the magnitude of F, multiplied by the cosine of the angle between the displacement and the force. So the magnitude of the force multiplied by the cosine of the angle between the force and the displacement multiplied by the magnitude of the displacement. So this is for any situation. So if an object is being displaced in a specific direction, and it can be an object on a surface, it can be an object moving in deep space, whatever it is. If an object is moving with a particular displacement, and there's a force acting on that object at an angle to that displacement, then the work done by that force on that object is equal to the magnitude of the force multiplied by cosine of the angle between the force and the displacement multiplied by the magnitude of the displacement. So this general equation here gives us a way of calculating the work done by any force at any angle to any displacement. So in the case where the force is parallel to the displacement, the angle is 0. Now what this means is the cosine theta part of this equation is going to be cosine of 0. If we do cosine of 0, we get 1. So when the force is parallel to the displacement and the angle theta is 0, the work done simply equals the magnitude of the force multiplied by the magnitude of the displacement, because cosine theta becomes 1. However, if we have the force acting at 90 degrees to the displacement, let's see what happens there. So 90. We take cosine of 90, we get 0. And so if the force is acting at an angle of 90 degrees to the displacement, this becomes 0, which means the work becomes 0. And so this is a general equation that allows you to calculate the work done by any force at any angle to any displacement on any object. And you'll see that the work done doesn't depend on the mass. There is no term for mass here. So one final example here. What happens if you have a situation like this? So let's say you have an object which is being displaced in this direction. Now again, what's causing that displacement is irrelevant in this context, because all we're interested in is if there's a force acting, what is the work done by that force. So let's imagine we have, and I'm going to pause here and let you guys have a go at solving this. So let's imagine we have here a block of 1.2 kilograms in mass. And let's say the displacement is, let's say 5 meters in this direction. But let's say that the force acting on this object in this direction is 20 newtons, and it's acting in the opposite direction to the displacement, as you can see from this example here. So let's say this is 20 newtons. So in this case, what is the work done by this force of 20 newtons? So I'm going to pause here and let you guys have a go at this. Again, if you're watching this on my website on the lessons page, the video will pause and let you have a go at this and enter your answer into the interactive question that pops up. If you're watching this elsewhere, pause the video and see if you can work this out for yourself. Okay, number of answers coming through here. A couple of people saying they don't know. Okay, so let's have a look at how this one is done here. Okay, so in this case, there's a couple of ways you can do this. Now, again, I'm deliberately avoiding using kind of vector notation, things like dot products and stuff like that, because at GCSE level, it's unlikely that you've come across it. We will be encountering that later on in the A-level course, A-level physics course, which is forthcoming. But for GCSE level, at least in physics, this is actually going a little bit beyond what you need, but I'm trying to get you guys to understand this at a deeper level. So let's have a look at this situation here. So remember, the work done is equal to the force, the magnitude of the force multiplied by the cosine of the angle between the force and the displacement multiplied by the magnitude of the displacement. So in this case, let's think about this. The displacement is in this direction to the right. So the displacement is acting in this direction to the right. But the force is acting to the left, which means the angle between the force and the displacement is in fact 180 degrees. Now, if you take the cosine of that angle, 180 degrees, you'll find that it comes to -1. Now, what this means is that the magnitude of the force F is 20 newtons. The magnitude of cosine theta is -1, so you now have -20 newtons, and you're multiplying it by a displacement of positive 5 meters. So if you have -20 multiplied by positive 5, you get 100. So the total amount of work being done by this force multiplied by this, the magnitude of that is 100 joules, but it is at -100 joules. So what does this mean? We've just calculated a negative work. So again, we have 180 degrees. This is our angle theta, 180 degrees, which means the work done is equal to the magnitude of the displacement, 5, multiplied by the magnitude of the force, which is 20, multiplied by cosine of theta, cosine of 180 degrees. So this gives us 100 times -1. So the work done is actually -100 joules. So this represents energy being taken out of this system. Remember, from the point of view of the person pulling with the 20 newtons, if you're thinking about a person actually pulling it, whatever the phenomenon responsible for this, for 20 newtons of force, the this phenomenon, this force, is removing energy from this object. It is slowing this object down as it moves from left to right here. It's taking energy out of the system. That's what this negative sign means. So this is an example of energy being taken out of a system, and because the sum total energy of this object, which was formerly moving, is less after this force has acted over this displacement than it was before, the work done is negative. There has been energy transferred from this object. So that's one way of solving this. Now, again, we could have thought about this by defining this direction from left to right, the displacement, as being positive, and therefore, in that context of left to right being positive, a force acting to the left is negative. So this would be minus 20 newtons if we choose to define the direction left to right as being positive. Now, in physics, it's very important for us, whenever considering any particular problem or situation or system, to define our coordinate system and our frame of reference, so that we know when we're in our equations, when we're talking about one direction versus another. In this context, the way that we've approached this problem, the cosine of 180 degrees has done that for us. And so understanding this equation, this version of the more basic equation that appears in GCSE curricula, W is equal to force times displacement, this is very basic. This assumes a number of simplifications. But by thinking of it in this more rigorous way, we have defined for ourselves an equation that allows us to calculate the work done by a force even at an angle, whether we're talking at a specific angle of theta or perpendicular or in the opposite direction. This equation allows us to calculate the work done, and it's always dependent on the magnitude of the force, the magnitude of the displacement, and the angle between those two vectors. So, speaking of negative work then, many of you might be thinking, oh, how can you have something like negative energy? Well, it all depends on your frame of reference here. So let me just finish off by defining a couple of terms that, again, we're going to be getting to this in later lessons in a lot more depth. And a number of you have asked a number of questions pertaining to this in the Q&A section here. So when I stop this video recording, I will be answering your questions in the discussion that follows this lesson. So let's define what we mean here. So this is going to be revisited in the energy topic, but since we're talking about work, it is important that we define our terms here. So energy cannot be created or destroyed. It can only be transferred and stored. So let's imagine we have a system with a certain amount of energy to start with. Energy of the system at the start, meaning before some change takes place. Now, what we're saying here is the law of conservation of energy says that provided that no energy enters or leaves that system, and again, a system is just an object or collection of objects that we happen to be considering, the total energy of that system at the end is equal to the energy that you started with. However, a system is a group of objects or an object which are applying forces to each other, which are in some way interacting with each other. Now, there are no closed systems in nature other than the universe itself. So when we're considering, for example, a steam engine, that is not a closed system because, as we saw, some of the energy from the chemical potential energy being released from the coal in the boiler ultimately does escape to the surroundings. And so the system itself is not a closed system. For a closed system, this is true. But for an ordinary system, for real systems, energy can enter the system from outside, energy can leave that system to the outside. And so we need to incorporate the energy transferred either into the system or out of the system into this equation. So this is true provided that the work done on the system from outside or by the system to the outside remains zero. But if work is done on the system, if energy enters the system, then the energy of the system at the end is higher than the energy of the system that you started with. So we need to adjust this equation to make it true. And the way that we do it is we add work to this side of the equation. Now, this is the external work, because it relates to energy transferred into the system from outside or energy that leaves the system to the outside. So we call this external work. Now, let's take a look at this equation again. So we're starting with a collection of objects or a system. So an example of this would be this object resting on a frictionless surface, and it's already in motion. And when we start to consider this system, it's at this point, and a force starts to act on it going backwards. This force is being applied by something external to this system that we don't see in this diagram. The arrow simply represents the pull to the left of 20 newtons. So this object is moving to the right, it's being displaced to the right, but this force is not responsible for that displacement. So this object may already have been moving with a constant speed when this force started to act. But nonetheless, while this force acts, it continues to be displaced to this point here. Well, this means that energy has been taken out of the system because the force, that force acting to the left, is slowing the object down, and so external work is being done. However, the external work in that example is minus 100 joules. Energy has left the system, and so the energy of the system at the end is less than the energy of the system at the start. So in that case, the external work is negative. So external work can be defined in two ways. It can be positive external work, and this means energy transferred to the system from the surroundings or from some other system. Now what this means is that the value of W in that case is going to be positive. Had we, rather than pull in this direction, had we pushed this object in the direction that it's being displaced, as we saw before in the previous examples, that would result in an acceleration. The object would gain kinetic energy, which means that the system would increase its energy so that at the end of that change, it would have more kinetic energy than it had started with. And so positive external work, when work is positive, has a positive value in joules, energy has been transferred to the system. Now, another way of saying this is that work has been done on the system. So you'll see this language being used. Work done on a system means energy transferred into that system by means of external forces or external phenomena. But external work can also be negative, as we saw in that last example. So if the external work is negative, energy has been transferred from the system to some other system or to the outside. So energy transferred from the system. And again, another way of saying that is to say that work has been done by the system on some other system or on its surroundings. Oops. Meant to underline the word by there. So, when the external work is zero, the energy that you start with is always equal to the energy that you end up with. Regardless of what has happened within that system, the total energy within that system is the same because nothing has entered and nothing has left. That is the concept of external work. Now, internal work is something else. So I'll finish off with this example to illustrate what we mean by internal work. So imagine, for example, you have something like, let me just go back to the title slide here, something like this enormous shipping container here. Let's say it weighs several hundred tons or whatever, some enormous weight by human standards. Let's imagine it's resting on the ground like one of these things over here. Or even better, a stack of them are resting on the ground. So let's imagine you now come up to that stack of shipping containers which are full of goods and heavy things, and you decide that you are going to push on that stack of shipping containers with all the force that you can possibly muster by just within your muscles, and you push and you strain and you push and you strain. But that shipping container doesn't move an inch. It doesn't move a centimeter. It doesn't move a millimeter. It doesn't move appreciably at all. The question is, have you done work in that situation? And it's almost a trick question. So have you actually done work in that situation? I'm going to pause and let you guys respond to that question in the chat. Again, think about that before you move on. Not sure why my cursor is lagging here, but I'll pause here and let you guys answer that question. What do you think? Have you done work in that situation? So you're standing here and you're pushing with all your might against this shipping container and nothing is moving. Now bear in mind, imagine actually doing this. Imagine actually pushing on this shipping container or a stack of shipping containers with all your might for several minutes. Think about how you would feel and what's going on in yourself. Okay, lots of a mixed bag of responses here. And again, I will be discussing this in the Q&A discussion after I close out this video recording, so don't panic if you're confused. Okay, so there's quite a few answers here. So the key here is that as far as the system is concerned, from the point of view of the pusher, the system is the object sitting on the ground, and from your point of view, you have done no work on that system. You have not moved the object. It has not gained kinetic energy. The system hasn't changed its kinetic or potential energies because you haven't changed that system. So from the point of view of external work, you have done no external work. Now, from your point of view, you have done internal work because you have pushed, you have strained, your body temperature has gone up, your muscles have lost some of the energy that they had before you started pushing. So internal work. Actually, I'm not going to draw a line to that because in this equation, W is external work. Now, internal work, at a very basic level, and I am simplifying here, internal work, this is energy transferred within a system. So, from the point of view of you as a system, you have done internal work because you have transferred chemical potential energy in your muscles. And you haven't actually transferred it as useful kinetic energy because nothing has moved external to yourself, but internally to yourself, that energy has been transferred largely as heat energy, which ultimately your body will radiate away into the surroundings. And so internal work is energy transferred within a system which doesn't affect the external characteristics of that system in terms of what's observable by an external observer. And so this is the distinction between external work and internal work. Now we are going to be getting into that in a lot more depth later on, but for the moment let's finish off here by looking at what happens to these objects after these forces act over these displacements. Now I mentioned before that the idea that when these forces act, so if we compare a force acting over a specific distance, let's say a small force acting over a small distance, then that object, as long as it's not, as long as this is the resultant force and there are no frictional forces slowing it down, that force, according to Newton's second law, will produce an acceleration. The mass will determine how big that acceleration is. The smaller the mass, the greater the acceleration, and the larger the mass, the lower the acceleration. But there is acceleration, which means that the speed has increased. Now, the kinetic energy, the mechanical kinetic energy of an object, is the energy which is stored by virtue of its motion. And so Kinetic energy is essentially what the energy is being transferred to. Remember, in all of these examples, we've been talking about work. It is the energy being transferred. So it's a certain amount of joules. It's a certain amount of energy that has been transferred from one store into another. But we haven't talked about what it's being transferred into, and so it is kinetic energy. So here is another one of these very useful simulations from our friends at PHET. So if I take this skater, for example, and I place them up here, the force of gravity that acts against this person. Now again, we're not taking into account friction or air resistance or anything like that. The force of gravity will do work in pulling them down the slope and accelerating them down the slope. And then their momentum will carry them in this direction, and the force of gravity will do the opposite. It will decelerate them. Now, this means that ultimately, if we consider a very simple situation where there's no friction and no acceleration, then energy is being transferred from one store into another. So we can think of the total energy of the system remaining constant because the system, the skater, the earth, and the slope, is not transferring any energy outside of itself. All of the energy remains as either the potential energy of the skater as they go upwards, increasing, and decreasing as they go downwards, and the potential energy is being transferred into kinetic energy as they accelerate downwards, and the opposite happens as they go up the slope. This is all being done by the force of gravity. The force of gravity does work in transferring the gravitational potential energy to kinetic energy as they accelerate down the slope, and it does work again in transferring their kinetic energy into potential energy. But this is a very simple situation where no external work is, there's no external work. This is all internal work within this system. But if we imagine now that there is friction involved, so now we have the friction between the skater and the ramp, and also air resistance, if we count that as a form of friction. Let's take a look at what happens here. So we have a certain total amount of energy at this point, and it's all potential energy because the person is not moving. But as they accelerate down the slope, the force of gravity is doing work in both cases, but some work is also being done against the force of friction, which means energy is being transferred ultimately into thermal energy in the skateboard, the bearings, the wheels, in the slope, and so on, and in the air molecules of the surroundings. Ultimately, all of that energy will be transferred externally as thermal energy, so that the system will end up with zero energy. And so this is the meaning of, this is a kind of example, a very basic, very simplified example of the difference between internal and external work. So a word on kinetic energy then to finish off here. So the formula for calculating kinetic energy is something that you probably have encountered already. If you haven't encountered it, then we will look over it in a moment, but I'm going to ask this question, see if you guys can answer this question here. So we have a sports car with a mass of 1,500 kilograms, and it's traveling at a speed of 70 kilometers per hour. Be careful with your units here. So what is its kinetic energy? So how would you calculate its kinetic energy? And I'll give you a simple conversion between kilometers an hour and meters per second here, just to save you a bit of time. 70 kilometers an hour, you can convert it by turning the kilometers into meters. So we have 70,000 meters. An hour is 3,600 seconds. Remember, standard units of time are seconds, because you have 60 seconds in a minute and 60 minutes in an hour. 60 times 60 gives you 3,600. So when you divide 70,000 by 3,600, you get about 19.44 meters per second. So I'm getting a few answers here. A few people don't know the kinetic energy equation, so I'll show you the kinetic energy equation, see if that helps. So we see here that the kinetic energy is equal to half times the mass of an object times its speed squared. So the kinetic energy is dependent upon the mass, it's proportional to the mass, but the effect of the speed of the object is much greater because you square the speed to get the kinetic energy. Okay, so let's substitute some values here. So we have the speed of the object, 19.44. We have the mass, 1,500 kilograms. We substitute those into the equation. We can evaluate, and we get a kinetic energy of about 283.4 kilojoules. So this is to two significant figures, this would be 280 kilojoules. Now, forces, as we saw, will accelerate objects, and we saw that in Newton's second law. We saw that in the examples of work being done by forces in these basic situations. So when a force moves an object, it's responsible for, when it's accelerating an object, it's responsible for raising the kinetic energy of an object. So in a car, for example, to increase the speed of the object, to increase the magnitude of its velocity, the driver will push down on the accelerator. This increases the driving force which drives the car forwards. Now, the way that this works is that more petrol is forced into the engine for combustion, and so more of that chemical potential energy is released as ultimately to give more mechanical energy to the car. Now, this is the sort of language that you need to be using in these descriptive contexts. Examiners increasingly want you to use the idea of energy stores, the idea that energy can be stored just as easily in motion as it can in position. Now, later we'll talk about potential energy as being the type of energy stored by means of the position or the arrangements of objects in a system, and the kinetic energy as being the type of energy, or rather the energy stored by virtue of the motion of objects in a system. So, you need to kind of get away from the more old-fashioned language of saying types of energy and think more in terms of a system stores energy in various forms. So when we write expressions like this, what we're talking about, the energy of the system at any given time, is the sum of its potential and kinetic energies. So before a change takes place where external work is done on a system or by a system, the system at the start or at any point, the energy of a system at any point is the sum of the kinetic energy of a system plus the sum of the potential energy of the system. Now, when work is done, one or both of these will change. If external work is positive, one or both of these will increase. If external work is negative, one or both of these will decrease. But at any given moment in time, the total energy of a system is always equal to the sum of the kinetic and the potential energies of a system. So in the car's engine, we start with chemical potential energy, and that is transferred into the kinetic energy store of the vehicle. So to slow down, the opposite series of changes happens, minus the idea of kinetic energy. So to slow down, the driver will push down on the brake pedal. This then increases the size of frictional forces acting in the opposite direction to the motion of the vehicle, and this transfers some of the kinetic energy of that system into heat and also sound energy, which ultimately goes off into the surroundings. And so we can think of this as transferring energy from the kinetic energy store of the vehicle to the heat and sound energy stores of the surroundings or the environment. Now, the driver could also just release the brake pedal, or rather release the accelerator pedal, and because the driving force decreases, and ultimately the frictional forces will become greater than the driving force and will then accelerate the car in the opposite direction to the direction that it's moving in. And so in that case, again, you still have frictional forces at work, even if you've not applied the brakes. You have the air resistance, you have the friction between the car and the road, the internal friction of the moving parts of the car. Ultimately, all of those will transfer the energy of that system from the kinetic energy store to the sound and thermal energy stores of the surroundings. Okay, everyone, that's going to do it for the recorded part of this lesson. I'm going to switch over now to going through the questions that have been asked by the students in attendance in the Q&A box. Thank you for watching, and I will see you in the next one. Take care.